When we talk about salt in the ocean or salinity, we're not simply referring to table salt dissolved in the ocean. What we're talking about is a list of ions that are presented here. The most common ions found in seawater represent all of the rocks and minerals that ever formed on the Earth that have undergone weathering or dissolution. Those ions end up in the ocean basins. If those ions aren't turned back into other minerals, either evaporite minerals when the water goes away, or incorporated into some melt to produce a new generation of metamorphic or igneous rocks, those ions will remain behind in the ocean basin. This is what we're looking at. For the most part, the ions are chloride ions and sodium ions. Sodium chloride being table salt, that makes sense. But also very significant are sulfate ions, magnesium ions, calcium ions, and potassium ions. These are all going to be important components of evaporite rocks. In the case of the sulfate ions, these combine with calcium to form anhydrite or gypsum. These are minerals that end up in drywall. So a very commonly used mineral there that is commonly associated with evaporating water. If you've been to any of the sodium sulfate lakes in the southeast of Saskatchewan, we're making sodium sulfate minerals out of these ions, sodium and sulfate, that are left behind when those lakes evaporate. You'll notice they're fairly stinky, and the stinkiness is from bacteria using the oxygens off of these sulfate radicals as a digestive source. They're anaerobic bacteria that use the oxygen from the sulfate to break down organic matter without the presence of molecular oxygen, like many bacteria would prefer to use. Now, when we look at the deep ocean, it's salinity that's driving the circulation of that water, of that deep ocean. It's the increase in salinity that is important. Salinity itself is the number of grams of salt dissolved in 1 kilogram of water. We refer to that as per mil, or parts per thousand. So when we're talking about salinities, we'll talk about a salinity of 32 or 36. That means 32 or 36 parts per thousand dissolved solids. Now, we combine the saltiness aspect of circulation with the temperature aspects of circulation. We end up with thermohaline circulation, temperature and salt-driven circulation. When we look at the vertical structure of the ocean, we can depict it in a couple different ways. In terms of temperature, if we were to drop a temperature sensor off of a boat into deep water, there'd be very little change right at the surface, then a rapid increase in change, known as the thermocline, the cline or incline in temperature, followed by a long, slow cooling, not to zero, really to 2 or 4, depending where in the ocean we're talking about. When we look at the salinity of the ocean, we'll see relatively low salinity near the surface with an incline known as the halocline or the salt incline here, where salinity increases. And then below that, we see a gradual increase in salinity all the way to the bottom of the deep ocean. When we combine the influence of temperature and the influence of salinity on the density of water, we end up with what's called a pycnocline. This pycnocline is the change in density from one depth to another. So again, here, right at the surface, we have very little change with depth. Then we enter the pycnocline. The change in density increases rapidly, is such that it increases rapidly. And then there's a gradual increase to the bottom of the deep sea, 5 kilometers down. So it's this pycnocline, this feature, the combination of temperature and salinity, that ultimately determines density, which determines the strength and rate of flow of deep water, the thermohaline circulation. When we look at the Western Atlantic Ocean here on the top, this is from 60 degrees north to 80 degrees south, essentially the northern tip of Scotland down to the southern tip of South America, a little past the southern tip of South America, actually. So what we see is the highest temperatures here located just to the south of the equator. Those temperatures are forming a circle here, or the center of a donut of relatively cold water that surrounds this gyre of warm water. As this Atlantic water circulates, it evaporates. As it warms and evaporates, it becomes denser. When we look at the Pacific Ocean, from 60 degrees north down to 80 degrees south again, we'll see a very similar feature. Again, centered a little bit south of the equator. The highest temperatures are going to be in the middle of this donut of colder water. This gyre in the Central Pacific is going to represent warm water because that water, as long as it stays at the surface, is exposed to high insolation and high evaporation. When we look at the Atlantic, we have a complication, and we'll call that Mediterranean outflow. Here, this Mediterranean outflow in salinity units shows salinities above 36 parts per thousand, which is a very high salinity for an open ocean environment. So this Mediterranean outflow represents something very different, something that's coming out of the Mediterranean that's distinctly salty. When we look at the Pacific, we have a salty region, again in the center. In this case, is due to evaporation in this location. This saltiness up here, the Mediterranean outflow, is due to an increase in salinity somewhere else, not here in the Atlantic, but way to the west. Well, I can't see west here, but say off in this upward direction towards the Levant, towards Lebanon and Cyprus and Beirut in the easternmost Mediterranean basin. So what's going on there? Here's a picture with Barbary ape. I'm standing on the top of the Rock of Gibraltar, which is technically owned by Britain, but it is completely surrounded by Spain, and it uses British currency. Yeah, I don't know why. Well, I know why, but anyway, so Africa is in the background here, standing in Spain or Britain, depending on how you look at it. And this narrow passageway here is the inflow and outflow of the Mediterranean Sea. So the Atlantic Ocean is over here behind the ape, and the Mediterranean Sea starts right about here, off to my right, which would be your left. And just on the opposite side of the water, standing in Africa, with Spain in the background here, standing in Morocco, Tangiers, the port is located right here, and the city itself, the Casbah, all that kind of stuff is located just over here to the right. So standing in Africa, looking at Europe, or standing in Europe, looking at Africa. Okay, after that interruption. So we're looking at the Straits of Gibraltar, which was formerly known as the Pillars of Hercules, from Africa towards Spain. Now, something's happening off here in the distance in the Mediterranean Sea that's going to influence what's going on in the middle of the Atlantic Ocean. And we could get a better feel for that here. So this is the Rock of Gibraltar. This used to be some insurance commercial, the Prudential, something like that. A very famous structure. It's been a long-term defensive structure in both world wars. It was important. In the First and the Second World War, it turns out to be very important for what was going on in the Mediterranean Sea. In particular, U-boat activity. The German submarines were getting into the Mediterranean Sea and doing damage and then sneaking out of the Mediterranean Sea. The mystery was the British were here watching the Straits of Gibraltar right here, and they couldn't figure out how the submarines were getting in and out without making any sound because they were powered by diesel engines at the time. Turns out they were using oceanography to sneak in and sneak out, in that salty water that forms over here in the eastern portion of the Mediterranean Sea sinks. It runs along the bottom of the Mediterranean Sea until it gets to the Pillars of Hercules, or the Straits of Gibraltar here. Then it slides out through this narrow zone here, which you can see here. So it's sliding through here into the Atlantic. Now, because it's salty water, it's on the bottom. Because it's flowing out, it has to be replaced by fresher seawater. In this case, normal salinity Atlantic seawater is sliding in along the surface. If you were a sneaky submarine captain, you would bring your submarine here, you would drop it down just a few feet below the surface, turn off your engines, and allow that inflow water to carry you into the Mediterranean. Then fire up your engines and do your thing. When you want to leave, you come back here, you lower your submarine to a greater depth, you can turn off the engines, and at that greater depth in that saltier water, just coast on out to the Atlantic, and you're free to move around the Atlantic Ocean again. So you'd not be heard going back and forth because surface water is going in one direction and the bottom water is going in another direction. So it's easy to sneak in and sneak out. Eventually people caught on. Now, if you are lucky enough to get to visit, you can take a cab or a bus up here. If you drive your own car, be aware that these guys will swarm your car, and they really love aerials, these antenna, and wipers. So they jump on the cabs, pull the antenna off, pull the wipers off, and throw them over the cliff. People inside are always astonished. It's worth checking out. Okay, so what's the result? When we look at the temperature of the Atlantic at a depth of 1,000 meters, we see an anomaly here. This anomaly, much warmer water, is the warm water that was ultimately heated up over here in the eastern Mediterranean, got salty, slides out, and because of its saltiness, even at that high temperature, it remains denser than the surrounding water. So it slides out as kind of a tongue of warm, salty water at a depth of 1,000 meters. When we look at the distribution of salinity at 1,000 meters below depth, again, we see what we'd expect to see based on that last image, very salty water coming out of here and then dissipating in the Atlantic. Now, part of it's going to be swept up in the North Atlantic Gyre, as you can see circulating here. Parts of it are going to be entrained in the North Atlantic Drift, in the Norwegian Current, and getting pulled and stretched to the higher latitudes here. So we have the Gyre doing two things here. It's bringing some of the salty water to the south, and the northern portion of the Gyre is going to drag some of that salty water further to the north. Now, this brings us to bottom water formation. Bottom water formation is going to begin when cold water, which is usually salty, gets colder. And because it's cold and salty, it's going to be more dense. And because it's more dense, it's going to sink. Ultimately, this water becomes the densest water in the oceans on Earth, and it tends to cruise around the Earth at very large depths in very deep water. Now, there are two ways to form this deep bottom water, this dense, deep bottom water. Sea ice formation. When seawater freezes, the salt is excluded from those ice crystals, and the net result is we have ice that isn't fresh. If you put it in a glass of water and let it melt, it would taste like salty water, but it's not as salty as seawater. The result is a simple budget, mathematical budget, is if you exclude salt from the sea ice, what remains behind gets saltier, much saltier. And in fact, it's called a brine at that point. So very, very salty water is left behind when seawater freezes, forming sea ice. Sea ice is different from icebergs. Icebergs, that means ice mountain. Those come from the land. Sea ice comes from the sea. Icebergs come from the land. Sea ice comes from the sea. I strongly encourage you to watch this video. I'll attach it somehow or put it in the module somehow. It's pretty cool. David Attenborough is narrating for the BBC, so you know what it's going to sound like and what it's going to look like. So good quality stuff, and it's very interesting as well. Okay, so this brings us to Antarctic bottom water, which you see in that Brinicle video. This Antarctic bottom water, known as AABW, forms in the Weddell Sea. The Weddell Sea is located here, adjacent to the Antarctic Peninsula, which is here. I'll show you some pictures of some work we did down here later on in the course. Those photos are going to come from along here. So up and over the mountains, from those photos, you'll see the Weddell Sea, and there's a lot of this sea ice forming. This is a picture from Christmas Day about 10 years ago. This is relatively fresh sea ice mixed in with some icebergs. These icebergs are coming from here, this glacier calving in the back. This sea ice is probably a couple years old. It's been freezing, melting a little, and refreezing over a period of time. It's flat. It's also known as pancake ice because it's flat like a pancake. Okay, this bottom water is going to form in the Weddell Sea and also off the coast of Greenland and Iceland. That's where most bottom waters form. Eventually, it's going to work its way into the deepest part of the basins. We saw that in video. I forget, part 1, I think, of ocean circulation, the ocean circulation video module thing. Once that bottom water is formed, it's going to cruise around in those deep, low spots in the Earth's basins, ocean basins. And by about 250 years, most of it's going to reach this region of the Earth. And it's going to continue to cruise around Antarctica for centuries. Much of the older water that has been circulating in the deep basins is around 1,200 years old. So it takes roughly 1,200 years for surface water to become bottom water, to travel around the world and upwell somewhere to become surface water again. It's about a 1,200-year process. Its position centered at the South Pole with no connecting land masses means that the ocean circulation around Antarctica is unimpeded. This means it can really get whipping. As a result, we end up with the roaring 40s, the latitude between 40 and 50 degrees, and the furious 50s, the latitude between 50 and 60 degrees south. As you might imagine, these are extremely strong winds, extremely large waves, and it's a result of unimpeded movement around the continent of Antarctica by this current. To give you a feel for it, you can take a ride from Ushuaia via an icebreaker, such as the National Geographic Explorer, to the Antarctic Peninsula. Now, we did this about 10 years ago, and this video was taken a year after I was down there, so I wasn't present on the ship for this, but we went through seas very similar, and I could say it's exciting if you're not used to being out at sea. Fortunately, I don't get seasick, but I was giving a lecture at the time. I believe 60% of the people were throwing up in their cabins, or what was reported to me later on. So they watched, but they weren't feeling their best. For myself, I had to lean or wedge myself into a corner with the computer so that I could work the mouse while being tilted on my side back and forth for an hour. This is a video of a cruise ship that becomes disabled off the coast of Antarctica. The video that you're seeing is being shot from the National Geographic Explorer, the ship that I took down to Antarctica, and then we took up to close to the North Pole on Svalbard to chase polar bears around. So we get an idea for what conditions are like in the Southern Ocean. Again, this is a full-size cruise ship. It's been disabled. I believe what happened was a wave, as you see here, smashed the engine room windows. And when that happens, all the seawater ends up in the electronics. So the navigation equipment's shot, all the communication equipment is shot, the controls are out. So the ship is pretty much left on its own. This is Leonard and John here, two of the guys that I worked with on the Explorer. What they're doing is they're firing a satellite phone with a rocket over to the crew of this ship because they don't have any communications. So they're getting a cell phone blasted over to them that they can use to contact the Argentine Navy for a tow into either the Falkland Islands or into Ushuaia. So again, this is a full-size cruise ship. Okay, now the rocket's been fired and you see the rope net connecting the two ships. That's John there. Now they're going to send the cell phone over in that along this rope network that they fired across to the other ship. We were lucky enough to get a chance to go swimming in the Southern Ocean. This water is about minus 1.5 degrees, which is a lot colder than ice water. It doesn't seem like 1.5 degrees makes much of a difference, but it's the difference between very painful and really, really painful. So we got to flop around in very cold water. There were penguins out here in the water, and a seal popped up by my feet to see what I was doing in the Southern Ocean. Up north, we have bottom water forming. As mentioned a few minutes ago, this is the North Atlantic Deep Water, or NADW. This water is a little bit more complex in the way it forms than Antarctic bottom water, in that it's not forming simply as a residual from the formation of sea ice. It's a combination of warm, dense Gulf Stream water working its way up to the high latitudes where this warm subtropical water that's been evaporating down here in the south cools off and sinks. Once it sinks, it works its way around Iceland. Remember, Iceland is a part of the mid-ocean ridge, the mid-Atlantic ridge in particular. It's going to represent a high point in that mountain range, which runs again from near the North Pole all the way down to Antarctica. So it's a barrier. It's a roadblock in deep water circulation terms. This water, again, reaches the high latitudes it cools off. As it's cooling off, becoming more dense, it runs into water from the Greenland and Norwegian seas that formed sea ice. So now we have a combination of tropical salty water coming up and cooling off, mixing with cold water that's forming sea ice up here. Those dense salty waters that are now cold sink and work their way down south. And this is just zooming in a little bit on the area of the North Atlantic, give you a better feel for the complexity involved here. We have Iceland, again, representing basically a gigantic series of volcanoes that are sitting on top of the Mid-Atlantic Ridge. And the Mid-Atlantic Ridge is going to be running down here underneath the Reykjanes Ridge. Rek means smoke. So like Reykjavik, the capital of Iceland, over here means smoky bay. Vik means bay. The word Viking comes from wike, to leave a bay, to go a Viking. So this ridge here is going to represent a submerged portion of the Mid-Atlantic Ridge. We don't see it from space, but if you were in a deep water current, you would run into it. It would be a complication you'd have to deal with. And we can see a bit of that here. Iceland sitting here. Greenland sitting over here. We have these two passages around Iceland. The Ermenger Current forms here, and it has branches that bifurcate around Iceland. One goes to the west, one goes to the south and east. Sometimes the one going to the west gets completely swamped and displaced by the East Greenland Current, which is running down from the north. Other times it dominates. And it's this back and forth play between the cold East Greenland Current and the warm Ermenger Current that determines the climate in Iceland. And as we'll see later on in the course, some very dramatic things have happened here over the past 2,000 years. Dramatic in terms of oceanography and dramatic in terms of Viking history. Why the Vikings have the reputation they have is partly related to what's going on in the deep basin around here. When we strip away 4,000 meters or so of water, this is what the world looks like. We got a hint of this early on in Ocean Circulation Part 1, where we drained the ocean away. So we end up with the mid-ocean ridge sticking up here as a positive feature, narrow bands of deep water on each side. Same goes with the Indian Ocean, not so much in the Pacific Ocean. Now, we can look at bottom water carbon-14 values to get an age of that water. Carbon-14 is a radioactive form of carbon. Unlike carbon-13 and carbon-12, which are stable isotopes, carbon-14 is a radiogenic or radioactive isotope. Because it's radioactive, it decays at a specific rate. And that specific rate is 1/2 of it will go away every 5,730 years, plus or minus 30 years. By looking at the amount of carbon-14 that's left in any given sample, we can determine how many half-lives it's gone through, how many of these lives it's gone through, and therefore how old it is. This is how we know that the oldest bottom water is around 1,200 years in age. It's been 1,200 years since it's been at the surface. And this brings us to the Thermohaline Conveyor Belt, a global image of it. This is a really simplified version of that, but it'll work for us. So we have warm water at the surface traveling to the north. It's moving through the tropics and subtropics here. It's getting warmer. It's getting saltier. It's working its way to the north. It's giving off heat up here, just like a radiator or boiling pot of water. That heat is going to the atmosphere. That water is now colder and denser because it's given off that heat. And it sinks and it travels back to the south and ultimately gets entrained in the Antarctic current, travels around Antarctica a number of times, and then it works its way into the Indian Ocean, back up into the Atlantic Ocean, or into the Pacific Ocean basin, where at some point it's going to upwell. And at that point, it brings nutrients from 1,200 years of age and decay up to the surface, and we get a phytoplankton bloom. Life is good. A little more realistic depiction here shows deep water forming here in Antarctica, the AABW. Deep water forming up here in the North Atlantic, the NADW. Those are the primary sources of our deep water. And again, once it reaches The Antarctic region, it's free to move around the Antarctic for hundreds of years, potentially. What happens if this flow stops? Has it ever stopped? Well, it gets cold. It gets really cold, and potentially it gets really cold really fast. This is a model from years ago depicting how much colder it would get at different locations on the Earth's surface if we turn off that heat transport to the high latitudes in the North Atlantic. So if we shut down the Gulf Stream, for instance, it will get much, much colder here. We go into very, very low temperatures. And these low temperatures extend all the way over Western Europe. So Ireland, for instance, would go from the Ireland we know today to Ice Age Ireland, much, much colder. And I could tell you they're not ready for it. Has this happened? Yes, it has. Happened during the earliest advances in agriculture. People just started to farm in Syria, a place called Abu Huraira, and they started domesticating animals. They were starting to look like modern farming communities. Just as they got going, the thermohaline circulation turned off, and they went back into an ice age, cold, dry climate in the Middle East, the Fertile Crescent, located around here, this region. So it got cold and dry enough here that people gave up on farming, they gave up on raising animals, they went back to hunter-gatherer lifestyle. And we can blame this on Manitoba. Manitoba was covered with water from the melting glaciers, the Laurentide ice sheet. As that melted, it accumulated at the foot of the glacier, and that happened to be where Manitoba, southeast Saskatchewan, northern Minnesota, northeastern North Dakota are located. They were underwater, under a lot of water. Okay, what does this thermohaline circulation look like when we view it from space and maybe take a dive into the ocean? And we're going to travel to the North Atlantic first. And what you'll see is water flowing from the subtropics and the tropics up to the high latitudes. Now we're running into this roadblock here, the Mid-Atlantic Ridge, located right here, the Rankines Ridge in particular here. This water working its way to the north runs into this, and it's deflected downward and then to the south. So now it's cruising along West Africa, around the Azores, down through the Central Atlantic, across the equator. It's undercutting the surface water flow, warm water that's moving up from the Namib here across the Atlantic, warming all the time. As this cold water moves down from the North Atlantic, it gets entrained in this current that runs around Antarctica. And again, it can continue traveling around Antarctica for hundreds of years. Ultimately, some of it's going to peel away and cruise off into the Indian Ocean. Additional water is going to peel away and cruise on up into the Pacific and the Atlantic as well.